All right, welcome back to 105. Thank you for joining me today. So today we get to start the first hard topic of C and what makes C, C. So we get to talk today about pointers. So pointers give you a lot of control. They're also the source of a lot of errors. So it's kind of like walking a tightrope over a pit of snakes a little bit. So I'm here to help you not fall into the pit of snakes so nothing bad happens to you. So first, we'll do a bit of a rewind all the way back to lecture 2. So remember, computers, they just store numbers. They store binary numbers more specifically, like a light switch. Either 0, it's off, or 1, it's on. So if we assume we have like a 64-bit number, which is 8 bytes, so always remember that there are 8 bits in a byte. So if we represent like as a whole number and then we want to compute what it is, so remember before we'd like in base 10 we had like the ones column, the tens column, the hundreds columns, the thousands column, We changed to base 2 and they just became like the ones column, the twos column, the fours column, all the way up to, if we have a 64-bit number, all the way up to the 2 to the 63, which is some gigantic number. So if we just have the binary number 101, what decimal number is 101 in binary, if we remember? I saw this? 5? Yeah, 5. So it's still under my rule. I can count up to 5. That's fine. So this is like 1, 1, 0, 2s, 1, 4, and then zeros for the rest of them. So this is the decimal number 5. So especially if we have 64 bits, turns out you don't really want to write 64 bits. It's a bit of a pain to write out and especially read. So if you were trying to see if like two numbers are different and you got 64 ones and zeros, and I said are they the same number or not, and they looked almost identical except for one, you'd probably have some difficulties with it. So decimal numbers for humans, computers like powers of 2, they are in binary, but is there something else we can actually use that might be a bit more useful for us trying to understand computers? So computers typically, a very useful number system is actually base 16 instead of 2 or 10. Seems to be more convenient. So the rules for like base 16 would work exactly the same. So for decimal, we have 10 options for a digit, so 0 all the way up to 9. For binary, that's 2. We only have 2 options, 0 or 1. For base 16, it means we need 16 options. So obvious ones would be 0 through 9, but what about the 6 other characters? How would I represent 10, 11, 12, 13, 14, 15? Well, turns out we can just borrow some letters. So we call the base 16 number system, we call it hexadecimal. And we just borrow letters to represent the values 10 through 15. Otherwise, aside from this looking a bit weird, behaves exactly the same as any other number system. So just goes in order. So 10 is A, 11 is B, 12 is C, 13 is D, 14 is E, 15 is F. Alphabetical, so at least we should know our ABCs up to F. So don't need to know anything more than that. So we called like a single digit in binary a bit. So in hexadecimal, that digit, which would be 0 to 9 or A to F, could call it a hexet, like a hex digit. No one actually does that. So they just call the whole number a hex number. So in C, if a hex number, so short for hexadecimal number, you'll see it start with 0x, and then anything after that will be in hex. So it will be 0 to 9 or A to F. And just like any normal numbers, we could just have like FFF1, something like that. So this is not going to be testable, but it will help you understand some output that happens. So like nothing in the exam will be like, hey, here's a hex number, what is it in decimal? This is only for you to just get a glimpse as to this because we will see it today when we talk about pointers. But other than that, same rules apply, we just have a different base now. Turns out why it's convenient is because each hex digit actually represents 4 bits in a row. So if we have 4 bits, well, we can represent 2 to the 4 different things, or 16 things. Turns out that's exactly what a single hex digit will represent. So 1 hex digit represents 4 bits, kind of convenient. Also, why it works well is because computers deal with bytes, so that is an 8-bit number, so 8 bits to a byte. So 2 hex characters actually represents a byte. So since they're 4 each, if we have 2 of them, we got 8. That's 1 byte. So now if we had a giant 64-bit number, we could represent it in hex. And since each hex character represents 4 bits, well, I only need 16 hex characters instead of 64, which is a bit better. So let's say everything else is 0, and I just have the hex number F4. So what decimal number would be F4? So all the same rules would apply. So if this was base 10, this would be like the tens times whatever the value is of this digit. Well, for hex, same idea. It's 16 times whatever the value is of F. Anyone already remember what the value of F is? 15. So it's 16 times 15. So that's the value of this, which is 240, I believe. And then plus, well, it's 1 times 4. So in decimal, this would be the number 244, which thankfully I got correct. But same number system, same ideas. We just have base 16 instead of base 10 or base 2. So if you hear anyone say things in hex, computers like hex, you'll mostly see any like low-level details about a computer in hex. So also remember about memory. So in memory, each address contains a byte. And here I have the same figure I had in lecture 2. So the value is in blue. If I just represent each byte as a whole number, well, it can be any value from 0 to 255. So here I have 8 bytes with different values. And below them, I have the location they are in memory. So this one's at 512,000. Then they just go up incrementally. So 1, 2, Why 512,000? I just made up a number. So there's no particular reason why I picked that. Just every bit lives at an address, and they're just numbers. So what I could do is, and what actually you'll see as the result of C, that C will give you, we will be accessing these addresses today and reading them and looking at them. So it turns out whenever C shows you an address, it shows it to you in hex. So this exact same thing I could write like this. So instead of 512,000, that's in decimal, I could write it out in hex. Turns out it's 7D000. That's enough zeros. So if you don't believe me, you can go try it out, because this would be 16 to the power of 0, 16 to the power of 1, 16 to the power of 2, 16 to the power of 3, and then 16 to the power of 4. So you can do that math and figure out that it is actually the exact same number. So questions about that? So when we see addresses, same idea. Each byte will live at some address starting at 0 going up to some gigantic number. Turns out when we actually get to read them today, they'll be in hex like this, but same things just apply, just a number. Everyone all good? More or less. All right, perfect. So remember, we also said that C will go ahead and pick a location in memory for you. So if you create a variable called like int x, that'll be somewhere in memory. So an int takes up 4 bytes, so it might take up these 4 bytes down here. So it might take up, so each address is the address of a byte. So 1, 2, 3, 4, and they'll all be in order like that. So a pointer is just the starting address of a value in memory. So when we did that ampersand operator, that is the address of, and that gives us the address of the first byte of that value. So for values that take up multiple bytes, like int x, it's always the lowest address. So it's always the first starting one. So in the prefix example, if we did address of x, it would be this value. It would be 7D0004. So pointers are actually a new type. We get a new type in this course. So if we have something like int x equals 1, we can't do something like int z equals the address of x. So turns out that the type of the address of x is actually x star. And how you read this is, well, we call this a pointer. So we say it's a pointer to an integer value. And a pointer is just going to be where in memory that variable actually lives. So each time we take the address of a variable, well, we add an asterisk to its type. So if we have int x equals 1, and we can do something like int star, and for the star here, we could put a space before it or after it. It's kind of up to taste. C programmers like to put it right beside the variable name, so they'll do int star z equals ampersand of x, and you're allowed to do that. So now z is a pointer to x, we would say, but really it's just storing the address where the value of x is stored. So we could do the address of z in this case. So then we would get the address of the address, and it would be int star star, which would be a pointer to an integer value, which is very confusing. Don't worry, this lecture is mostly set up so that we get some exposure to it. We can ask questions. We can go through lots of examples later. So you can only take the address of a variable because variables are, by the C standard, need to at least appear to be stored in memory, and a value by itself, so if I just write the value like 1 plus 1 or 1 plus 2, those ints 1 and 2 might never actually be stored in memory. Only variables are stored in memory. So that means if I try something silly, like I take the address of 4, well, you get a very, very unhelpful message, and this is an especially bad compiler message. So we could have int x, actually, let's just say int star z equals the address of 4. Now there's a red line there. If I compile it, I get something very incomprehensible. It says cannot take the address of an R value of type int. What in the hell does that mean? I have worked on compilers, and I can tell you, even to me, that message sucks. So that message should probably actually say you cannot take the address of a literal, you can't take the address of 4, something like that. That would probably be more helpful. Yeah?
Could it mean that like our value is like whatever's on the right side of like an expression? Like so basically, because a 4, even if it was, say you did like x plus, like say you had variable x and variable y, you did add yourself x plus y.
Yeah.
Like maybe like the error message trying to be like as.
I kind of get what the error message seems to think that if it's an int, we can't take the address of it, but I mean, that's kind of silly because if we have this, the R value is an int, I can take the address of it.
Yeah, okay.
So yeah, it turns out it's just a bad error message. It's terrible. But so if you ever see some message you can't comprehend, it's because you tried to take the address of like just a random value. So don't do that. Again, this error message is beyond terrible. And then question, should we put 6 digits for hex numbers, like 6 zeros if the number is a 0? I'm not sure what that means. So hex numbers are just like any other numbers. If we have like a set size they have to be, they get leading zeros like anything else. All right. So in order to use a pointer and get the value it's pointing to back, we can use a star operator, which is a unary operator, to access the value at an address. So if we have int x equals 1 and int star z equals the address of x, that means, well, z currently has the address of x stored in it, and we can do star z, and star will go ahead and get the value at that memory location for us. So star z will take the address that's currently at z and then read the value that is currently pointing to. So in this case, we'll have a better worked example coming up, but since x is equal to 1, the z would be pointing to that value 1, and then we can go ahead and read the value that z is currently pointing to, which in this case is 1. So after the statement y equals star z, we would have y equal to 1. So you can also kind of reason about that each time you use the star operator, it removes a star from the type. So if I have the variable like int star star z, or we have a pointer to an integer, if I have just an expression star z, the resulting type of that is just a pointer to an integer. So each time you dereference it, which I probably shouldn't say because I haven't said dereference yet, you just remove a star from the pointer type. So here's a more worked example, just so it makes it a bit more clear. So we can actually also change the values of variables through pointers. So let's start off with this little example. So we have int main void. So when we start running it at main. So our first line is just int x equals 1. So we're declaring a variable called x and assigning it to 1. So in this bottom here, I will just have all the variables that live within main that are currently in scope like we had yesterday. So in main, after that line, I have an x, and then also in the blue square is going to be the value of that variable. So now I have x equal to 1. Everyone good? All right. So then I declare a y, set it equal to 2. So after that line, I have a y, and its value is 2. Now I have int star z, so this will just declare a variable called z, which is a pointer to an integer, and it is going to be the value, initial value is the address of x. So this is why we call it a pointer. So we don't really care about the actual value of that address. It'll be like that random 7D004 maybe. Who really cares? We just care what value it's actually currently pointing to and why we call it a pointer. So instead of doing the value, we draw this arrow. So this arrow means that the address that is currently stored at z is currently pointing at wherever the value of x is. And you can also kind of think of this as like a remote control if you want. That's one of the ways I learned it. So instead of going ahead and changing x directly, we can change x through z because we can access the value of x through z. So now if I have the line here, I dereference x, so that means I access the value that z is pointing to, and I change it to 3. So in this case, each time we do the star, which is called dereferencing, so accessing the value at, I would take z, see what address it is pointing to, and then I know this is the value I'm modifying because, well, I have to modify an integer, and this value is currently an integer. So if I do that, I'm immediately changing x. So I change the value of x. If I wanted to go ahead and print x now, I would see that I printed 3. So any questions about that one? Or fun things we want to do with that? Pointers are real fun. Yep.
So the pointer, like star z, the pointer would directly change x if I set the pointer equals the address x, right?
Yep.
So if I change any value for star z, it will automatically change x.
Yes.
And output the same number as z, right?
Yes. Yeah. So, well, not the same number as z, the same number of the value at z. Yeah.
You first.
Oh.
Can you quickly re-explain dereferencing and what it means?
So this dereferencing, so that's just accessing the value that that variable is pointing to. So if I have a dereference of z here, it means, well, I'm not using z, I'm using z to figure out what I need to change. So in this case, I need to change x because it's pointing to x. Yeah.
So actually, yeah, following up on that. So I guess like in this case, on this line that you're currently on, you kind of have like an expression on the left side of an assignment operator.
Yeah.
It's like a very like rare occasion, I guess. Or like
You're allowed to do it for the left side because you're essentially saying, well, this is the thing I want to change, and it's basically a variable.
Okay. So my original question was like, it means that like all the pointers to whatever they are, they're all like technically of the same size. They're just to the size whatever the pointer size is.
Yeah.
Like, just like, I don't know, 4 8 bytes.
Yeah, all the pointers, so everyone has, like, you've probably heard I have a 64-bit CPU. Everyone's probably heard that before. It means your pointers are 64 bits. So that's how big they are. So, yeah, so what's the application of it? Let's go here. So let's just make sure that we can go ahead and change it. So let's have that example written out. What I do, I said z equals 3. So now if I want to show that I actually changed x through z, or z, forgot what country I'm in, I can go ahead and print off the value of x. Oops, I can type compile too. So in this case, I see that x is indeed 3, so I'm changing it through z. And then, yeah, some other questions. Can I initialize a pointer without using an ampersand, like z equals 5? So if you do that, that means you're just randomly pointing at address 5. I think C will probably let you do that without complaints, and which is why I talked about the pit of snakes. So this is an instance of the pit of snakes. So C will gladly let me do something like that. It gives me a little bit of a warning saying that I'm converting to a pointer, so I'm converting an int to an int star, but happily lets me do that, and I will blow off my leg by getting a segmentation fault. So this is probably the first time you've ever seen that. This will be very common. So you basically see a segmentation fault every time you access memory you shouldn't be accessing. So in this case, I picked the random address 5 and said, please access the integer at location 5, and turned out that that was not valid. And the error you get when you run it is called a segmentation fault, which, if you want to know how that works, you will figure that out once you take 355 in the operating system course. So for now, you should always just take the address of a variable, and then you're guaranteed that the memory address you get is actually valid. And yeah, it will be represented as some gigantic hex message. And yeah, why is it useful? Well, we had to use it for scanf, right? Because with scanf, we did something like we defined an x, and then we did like scanf like this, right? Whoops. Scanf Yeah, we did something like this, right? Because after scanf ran, it changed the value of our x. So how did it do it? Well, the only way it could do it is through a pointer. Because remember, function calls, they pass by value. So if I just did something like x, it gets a copy of 1 and won't change anything. So we had to give it the address of x to tell it what it can modify. So it can go ahead and modify our value of x for us. And we can do that through a pointer. So now, hopefully, the mystery of why we had to do the ampersand for scanf is fixed. And here, again, if I just randomly said z is 3, that'll blow up too. Like, basically, you're going to have to guess a valid address, which is fairly hard. So, and we'll actually print off some addresses in a bit to see the ballpark of what they're in. Other question. So without the asterisks, I'm not sure which one you want me to delete. Like here, like z equals 3? If we do z equals 3, well, nothing's going to happen. So we create a variable called z, which is a pointer to an int. We get the actual address of x. Who knows what it is? And then we just say, OK, the address is now 3. Nothing bad happens in this case. We're just changing what address z is. But if I did something like this, that's bad because ampersand z would try to access the value at that memory location. So whatever the integer that starts at memory address 3 is, and then it just dies. So I can go ahead and run this if I want, and segmentation fault. Yeah, z is straight up another type. It's star, so it's a pointer to an integer. And again, if I tried to make like z an integer and compile it, C actually lets me do such a thing, but it gives me some warning that like, hey, you're trying to convert a pointer to an int. I did that for you, but you probably didn't mean it. And in this case, well, x is going to be just fine, even if I do like change z. Because now I just made z some random value and then reassigned it to another one. If I want, I can print z if I want. The output would look weird. So here, I can print z. It tries to do some conversion, so it tries to take some large hex number, basically, and then try to represent it as an integer, and you get some random crap. Yep.
If you like say z is like address of x, and then you go to the next, if you say go to the next location in memory, basically, at like whatever, like could you get to y somehow without explicitly specifying y?
Yeah, so if you really wanted to, you could get to y somehow by knowing in what order variables get set out in memory. Yeah. So you could.
But like, would that does C just do it like sequentially, or is that like compiler just like shuffles it around?
So it depends on the CPU, some data structure that we don't know yet, and you're not guaranteed it'll always be the same. So we'll see once we start talking about another data structure, basically how to do that. Yeah, so just changing z, here, just changing z to just some random value, that's going to change the address that z currently is pointing to. And if I just change it to a random address, trying to use it, probably not going to work. So if I do this, then currently the address that's stored at z is the start of variable x. And if I dereference it, that is going to be the value that x is currently pointing at. If I want to point to something different, I could point at y. And now y will change from a 2 to a 3. I can print out 3. Yeah, so there are some things you can do. Ill-advised, not guaranteed to always work across all CPUs. Yeah.
Well, if I declare like a constant outside of like main or something, like a global variable, I can also get its address, right?
Yep, yeah, if you create a global variable, so I'll call it G, you can also get the address of G if you want. That's fine. Yeah.
So can you do something destructive, or will the compiler always save you the segmentation for? Like, can you access a memory address?
What?
Like, because you have access to your entire computer's memory, right? So could you like
Oh.
actually mess up?
Oh, yeah, so that's a good question. That is a question I ironically just got asked today in the operating system course. So, yeah, since I can access memory, does that mean that, hey, I can just guess a random memory and then I can read my bank account information or something like that? The answer to that is no, your operating system is very smart and very secure. So you can't do that through mechanisms I will not even begin to explain now. But if you want to know, hey, you can look at the operating system course I'm teaching if you want. But it looks like you can access all of memory. That's just an illusion. Yeah, so any behavior you see with just playing with pointers, not guaranteed to always work, and that's why you can easily blow off your legs with a shotgun. So let's step through another smaller example. Here, we'll add a function call in the mix. This probably looks a lot more like scanf. So I'm writing a function called set3, takes, well, in this case, I'll say a variable called p, which is a pointer to an integer, and what it does is it tries to access the value that p is currently pointing to, and then set it equal to 3. So in my main, I'm going to start off again by declaring a variable called x, setting it equal to 1. So in main, x would be in scope or valid to use, and we can go ahead and that's it, just set to 1. Then we have y, we create it, set it to the value to 2. Then we have z, so that's the address of x. So it will point to the location that x is in memory. Again, all my blue boxes here are bytes that are currently in memory. Now I'm going to do a function call to set3. So remember, C is call by value. So this set3 function is going to get a copy of z, and it's going to copy it to the argument p. So we'll start a new scope. It will be called, well, in the set3 function, and we get p, which is a copy of z in this case, and it's also an address, and it points to the same thing. So the address has the same value. Remember, an address is just the starting location of, in this case, an integer. So we would copy it, and it would end up pointing to the exact same thing. So this is a way to get around that scope rule, because remember, in set3, well, I can't access x, I can't access y, right? Normally, can't access it in a different function. But through a pointer, I can access it. So here, I can now access x in the function set3. Now, after this line runs, well, it's going, since p is pointing at this location of memory, which just has the value 1, it can go ahead and change the value from a 1 to a 3, and then that function is done, so there's an implicit return at the end of it, and we'd resume from where we left off in main, then hit return 0, and then our program would be done. And yeah, this is the recommended way if we want to go ahead and use variables and try and change them in different functions without actually using a global variable or anything like that. But sometimes, if you don't have to, you don't really want to use a pointer because, well, some find it a bit weird that the value of x just kind of changed here. And yeah, this is same thing as doing my dereference of z in the previous example. I just moved it into the function so we can kind of combine last lecture, review it a bit with this one. So things are still copied by value, but now I'm copying an address instead of just a value. But an address, turns out, it's just a value. So this is why I told you about hexes. So we can actually print the address of a pointer if we want to. Format specifier, it's a new one. It is %p, p for pointer. And it expects a weird looking type. So void star, which knowing what we know so far, that's a pointer to nothing. So turns out void star is basically just C saying like it's a generic pointer. I don't actually care what the value is, and you're not allowed to access it. It's just saying it's a pointer. I don't really care what value type it's pointing to. So the rule is, well, you can't dereference it because if we got rid of the star, then we would just have void, which is nothing. So we can't dereference a null pointer, or sorry, not a null pointer, a void pointer. So the other rule is that you're allowed to cast a pointer of any type to void star. So if I have an int star, a pointer to an int, I can say, okay, it's a pointer to an I don't give a fill in the blank. So how that looks is I can just do the same thing, except I can print values. So let's see the exact same thing. So here I'm just going to print the value. So I have an x, I have a y, and then z is currently pointing to the address of x. So here I say x, so the address is this, so I have to do an explicit cast to make my compiler happy to avoid star, but it's the address of x, so this is a pointer to an int, and I just make C happy by saying it's a pointer to I don't care, because that's the type that %p wants. Then I just have equal to whatever the value is. Same for y. Then I do a set3 with z, which is the address of x, and then a set3 of the, just straight up the address of y. And then here, I'll print off the same things after I call set3. And then in set3, I'll print off the address of p, which would be a pointer to an int. So that's just the address that the argument lives at. And then the value of that pointer, which, well, since it's copied by value, it should match z, and it should match the address of y. And then here I print off the value at the memory location that p is pointing to by doing the dereference, which in this case, it would be an int. And then I'll go ahead and just set it equal to 3. So if I run that, I should see a bit of consistency here. Print. Let's make that bigger. So this is where I showed you the hex things. So these are memory addresses. They're just very large numbers in hex. So don't need to worry about them other than they're consistent. So it turns out that x is at this location. Its value is 1. Y is at this location. Its value is 2. P is at a different location because, well, it should be stored somewhere else in memory. And its value is this. So that makes sense because the first time we called it, it was z, which was the address of x. So this matches the address of x. And then we just changed, and currently the value was 1 because we haven't changed it yet. Then after this line, we went ahead and changed it. Then P, turns out its address is the same as before. Doesn't necessarily have to be, but in this case it will be. And then its value is this long ass thing, which turns out to be the address of y. So these two are the same, which makes sense. And well, the value at y before we modify it is 2. Makes sense. And then we modify it. The address of x never changed, but its value changed to 3. The address of y never changed, but its value is now 3. Whew, what a whirlwind. All right, we're good with that? Ish. So don't worry, pointers are hard. So just to color it, to see that what is consistent. So red is the address of x, so it's the address of x. It's the first argument we gave to the function, so it was the value of p. And then, well, the address doesn't change at the very end. And then in light blue, we have the address of y, so it was the value that we gave p for the function call, and it was still the address of y afterwards. And then here, I just put the address of p in different colors because in this case, they were the same address, but in general, they don't have to be. So, questions about that? All right, we should be able to now,
Yeah, just if you could add like another variable after y, would its address also like, because like x is 38, y is 32, if you add another one, would it be 30?
yeah, so it turns out that on a specific CPU, these go sequentially, well, sequentially down. So if I made another int I, something like that, yeah, I would get the address, same thing, except it would be 30. But turns out you can't rely on that. That would just be for this particular CPU architecture. All right, so should be able to understand that now and why that actually swaps two values. So let us simulate. So here is our swap function. So we should now understand that, hey, it does indeed swap around A and B. So if we start executing it, we would execute at main. We'd have this line, so declaring an integer called A and setting its value equal to 1. So here, we'll do the same thing in the slides. In scope and main, we'll have A, and its value is going to be 1. Then we'll have B. It's a new variable. Its value is going to be 2. Then when we hit this print line, what's the value of A and what's the value of B? Yeah, A should be 1, B should be 2, because, well, that's what we just set it equal to. So hopefully pointers did not break you so far. So up until this point, we haven't used pointers. So before, we'd see before swap, we'd see A is 1, and B is 2. But now we're going to do swap the address of A and the address of B. So since things are copied by value, we're doing a function call to something called swap. And up here, we'll use the argument name. So just to keep track of where I came from, I'll put a 1 beside this arrow to know I have to go back there after I'm done with the swap function. So in the swap function, it will have a variable called A, which is just some address. And it's pointing to, since it's done in order, it's the same as this. So it is pointing to mains A. So it's pointing right here. And then we would also have B, which is an address. And it's pointing electrical whoop. All right, and it's pointing to B there. So we're good with that so far? All right, so next thing we do in swap is create a variable called temp. And then its value is the value at swaps A. So because there's just one star, or dereference if we want to use that fun term, that is not in the slides, I go ahead, I follow A. Let's take a highlighter. I follow A it points me to an integer, and then that's the value I want to use. So temp would be equal to 1. And then, next line, I'm going to be modifying the value at A and then using the value at B. So the value at B, which is here, the value at this B is currently 2. So I'm going to change whatever A is pointing to 2. So it turns out A in swap is pointing to the value 1. So I go ahead and I change that from, oops, delete, from a 1 to a 2. And now, next line, I'm modifying what swaps B is pointing to, which is this value of 2, and I am assigning it the value of temp, which is just simply 1. So now, B, or this value would switch to 1. Now, we're done with this function, so they could have written a return here, but the compiler will implicitly put one there if you didn't add one. So it just returns from where it came from. So we resume back here. So we can go ahead and just remove the 1. We know where we came from. Now when we print main after swap, well, swap is now gone, so I can delete it. So now I just have that. And now when I print, I'm going to get main after swap. Almost wrote A is 2, B is 1. Whew. So questions about now how the swap function works. So it actually swapped the two values for us because we used pointers. Didn't have to resort to using globals or anything like that. Yeah, I don't really need to comment much more. So any other questions about that? And the question is from the line, so from this line, does it take the value, this value, at the moment of declaration? The answer is no, it doesn't have to. But in this case, well, we set A based off the argument, and then we take the value at whatever the value is it's currently pointing to. So if we go ahead and we called swap again, well, in this case, we'd be pointing at the same things, but I could swap the other order. I could do swap the address of B and then swap the address of A, something like that, and just swap it, but swap it in the other order if I want. So same thing will happen, but now A will be accessing mains B, and B will be accessing mains A, which might be a bit weird, but again, doesn't really matter about the names of the arguments. They just always get copied. But if I called swap again and just change the order of the arguments, doesn't really matter. And if I call swap 2 times, well, I swap and then I swap back. I'll get the same result at the end of the day. All right, any other last minute questions? Sweet, if not, I will take up the rest on Discord if there's anything else. So just remember, pulling for you, we're all in this together.